going on there. All right, so it takes 5 minutes to do that. I got to sort out something with a live stream as well, so we'll jump back in at 5:30. We're going pretty fast as well, so feel free to explore the notebook in a little more detail. Okay, so what might be easier to read than the docs, although it's good to understand this from scratch, is this cell inside the practical. So if you go to the portal, access the practicals, and open that visualize BERT embeddings practical, scroll down a bit past the stuff which we'll come back to, but here's a good template for using a tokenizer. So you can go from transformers, import the tokenizer that you want. There's loads of different tokenizers available. This is the one that's used for that model BERT, which creates representations of text that we'll look at in a second. And you can get that from the pre-trained weights just by specifying the model name. You can follow this pattern for loads of different tokenizers in Hugging Face, but this will give you a tokenizer which can be called on some text to encode that text into different tokens. So where's the name? The name is BERT base uncased. That's the tokenizer that you probably want to work with. So take a look at that. Take a look at that notebook. And then take a look at the Hugging Face documentation. See if you can do some of these steps. We haven't got that much to get through today, so we should be pretty relaxed. If anybody wants to dive into anything else, me to show an example, we can do that. And I'm not joking, one of you gets this. In an hour. Yeah, go for it. We'll come back to that in a sec. Yeah. I just want you guys to get hands-on with the tokenizer before we move past that. So in this practical, it mentions, you can see above, we're using this BERT model that I've mentioned, but and we'll come back to that in a second. But down here is where you get a chance to use the tokenizer. Cool. Has anybody else been able to answer this question? Sorry? Anybody able to answer, how does the length of the tokenized sentence compare with the input sentence? Yeah, so which one's longer? Yeah, absolutely. So hold that and we'll come back to why in a second. But can somebody help me tokenize it first? So I've got this BERT tokenizer. Dot encode. Yeah. So where would I find that in Hugging Face docs? Let's do tokenizer pre-trained. See if we can find that. These docs are not great, I don't think, or at least I'm not used to using them as well as I should be. But let's see if we can find that in here. Pre-trained tokenizer. What's this encode method here? This is the one that you want to use. So you can see this encode thing here is a method of the pre-trained tokenizer above. And what that means you can do is you can use all of these methods below. And the one here is, yeah, pre-trained tokenizer encode. So if I do encode the sentence, and then let's say I print that, tokens is equal to this, and then print the tokens, and run that. we need to run the cell above. This cell actually downloads the model as well, and you can see all of this happening here. Back here, print the tokens. So there are the tokens. Those are the different unique IDs, essentially, of the different tokens that I've got in that input sentence. Hello world and welcome. That is a 4-word sentence. This clearly has 6 different tokens in. So what's the difference there? Why is one longer than the other?
The start is usually something the start is to not those out.
Yeah, that's right. So if we were to decode that tokens, I think we can just do this as such. But tokenizer dot decode tokens and then print that. But tokenizer is not defined. Then you can see you've got this CLS and SEP on the end. Roughly, CLS represents the start of sequence token, sometimes the SOS token, and the SEP represents the end of sequence token, or EOS in some data sets. But the way that BERT's trained, it has these different named tokens, but the way you can think about it is they just represent the start of the sequence and the end of the sequence there. And that's why this 4-word sentence comes out as 6 different tokens. Play around with that. See if you can get it to come up with some other special tokens. Can you get it to produce a unknown token for a word that it doesn't recognize? And can you get it to produce a subword token? So like part of word, like I had earlier, quickly, had quick and ly. And they were 2 parts of the subwords. You could tell that ly was the end of the word because it was hashtag ly. So see if you can find some other examples with that, playing around with that tokenizer.
How can you print a number of words in the sentence? So that's kind of unrelated to the tokenizer, right?
Yeah, simply len sentence.
Would that work on a string?
It won't work on a string, or len sentence dot split. Something like that. Yeah, I mean, you don't really need to do this programmatically. It's just to demonstrate that it's a little bit longer. So another question for you guys to figure out now is, what does it do to different punctuation? What does it do to emojis? What does it do to capitalizations or misspellings? See if you can figure those out. Common misspellings, uncommon misspellings. Mm-hmm.
Yeah, so the decode will combine the tokens together if they work on this.
That's right. Yeah. So the decoding of the tokenizer, the decoding of any tokens will not only convert those token IDs back into their text representation, but also combine them all together into a string. Make sense? You look confused.
Yeah.
You look puzzled.
Is there an easy way to keep them separate?
Yeah, there is. So in the tokenizer, the put tokenizer has a bunch of different useful methods, including convert IDs to tokens, convert tokens to IDs, which I believe works in that way. So let's take a look at that. So there's the list of the separate individual words. So the decode is basically is doing that and then combining them. Essentially this, almost roughly. It's joining them together. Tokenizer can do a bunch of other stuff too. And I think the next thing it can do will actually relate exactly to this section, which is what is a vocab. So a vocab is the assignment of this integer index to each token. So for each token to have a unique representation, we need to begin to make it more mathematical. The first step there is to represent it by a index. So each token has a particular index. And that mapping between the word and the corresponding index, we call that a vocab. You can see when I do BERT tokenizer dot to get its methods and attributes, there is a get vocab method. Where is it? There it is. And if I print that, you'll see that you get this dictionary between all of the different tokens, which BERT has a representation for, and a unique index. In this dictionary, you can see there's a lot of unused tokens. Those ones are basically spare spaces left in BERT's memory that you can use to either add your own tokens or do something else with. But beyond those, you get at the beginning some special tokens. Well, all special tokens, you can tell them because they're enclosed in square brackets. You get things like the padding token, which is used for making sentences the same length when you process them. If you scroll all the way down past these unused tokens, we'll get to the real words. And it's too long. It's too long to print there. BERT has about 30,000 word representations in its memory. And what we're going to do as we go through this practical notebook is get to looking at what are the vector representations for each of those word representations. And hopefully, if the visualization works well enough in Colab, because it's sometimes temperamental, we'll be able to see the 3D plot of how different words are represented by BERT. Hopefully in a way that similar words appear in similar places. Cool. So let's move on to that then. So we've looked at so far that we've seen the corpus, the tokens, the tokenizer, and the vocab. And those are essential things to understand for all of the pre-processing that goes into natural language processing. And then beyond that, we've seen that we can represent words as indices. So we take a word and we give it a number, which basically represents, which number word is this in my set of all my unique tokens. And that's the index. An alternative way to represent that is like this, as a one-hot vector. So you might hear about this or see them in some places. One-hot vector is 0 everywhere except 1 in the position corresponding to the index of the item that it represents. So this represents word number 2. 0s everywhere except for the 2. This is a way that we can begin to make the words a little bit more mathematical. It's not particularly more useful than an index, other than the fact that it shows that words are not on a single scale. Word number 1 is not smaller than word number 100 because they're just not on that same number line. So this is a little bit more useful of a representation for the words. It shows that all of the words are different. They don't line up on the same axes. But if we represent all different words like this with a one-hot vector, what's the problem with that? Why might that not be the most useful representation? Any ideas? Exactly, yeah. So that's one big reason. We could have huge, for every word, we need to add another item to this vector to store the representation for each word. If I've got 30,000 words, or something like 130 in the English language, then I'm going to have that long of a vector. So with increasing words, I need to increase the dimensionality of each vector to represent that word. That's one reason. Any other reason why this might not be the most useful way to represent words? Yeah. Yeah, that's a good point. So yeah, so the specific case of pluralized words or the same word, maybe in a different tense or something like that, those things are represented as totally different words. There's no similarity at all. If you do an element-wise comparison between the two words, then there's as much match between those very similar words in practice and totally different words. But the generalization of that is that basically every word, every different word, every different token that you want a unique representation for, they are all totally as dissimilar as one another from any other word in the dataset. Very similar words are not represented by very similar representations. And it makes sense that they should be. If I have two words that I want to kind of produce the same sorts of responses from a model, or two sentences which say the same thing in a different way, I probably want to represent them in a similar way. So we want to move on from one-hot vectors and address those problems. And the approach to that is to move away from this visualization of one-hot word embeddings, where each different word is represented on a totally different axis, and the dimensionality of your space is as big as how many words you have here. I've got 3 words in my corpus here. That's a 3-dimensional space. I want to move away from that to provide a more rich representation of the word, where the words which have similar meanings have similar representations. And that, to Dalia's question earlier, is what a word embedding is. So a word embedding might look something much more like this. In this case, I've got 4 different words represented in a 3D space. That is, each word is represented by 3 numbers, and those 3 numbers are not just ones and zeros, but they can be any real value, such that similar words should appear with similar representations. And that is what a word embedding is. So comparing one-hot word embeddings to these new dense word embeddings, you can see that we've got the one-hot word embedding on the left, and a dense embedding, typically this is what we refer to when we say a word embedding, it might be something like this. It's full of values, and each of them, like the activations in a neural network layer, hopefully they represent something high level, meaningful, and abstract about the word. They represent the information of the word compressed into this vector representation. And typically we have maybe 300 dimensional word embeddings or 128 dimensional word embeddings. The bigger the word embedding, the more information you can represent about the word in that embedding. So I'll pause there for a second. I need a drink. Any questions? That?
So the dense word embedding, like one vector, the representation of the vectors which are on like board now, these are one vector, right? They are represented here as if they're just like a 1D vector.
These are 3D and 4D vector. So 3 vector and 4 vector.
Okay, but sorry, but so wait, say
Mic's on, testing.
when there are those embeddings, then each word would have like high dimensionality, right? Like, so how many numbers is the word represented by?
This is a single word. That's a great question. So what I'm talking about here is that each of these vectors represents one word.
Excellent. Okay, so it's like 4D representation of one word.
Exactly, yeah.
And that's a comparison, I guess, or that's an example?
This is just an example. I think Bert has 1,000 dimensional embeddings or something like that. Yeah,
So
we'll take a look at that in a sec.
Complicated ones, you will have many numbers describing that one word.
Exactly, yeah. And so hopefully they represent some high level concept, right? So maybe that 16 is like how positive is this word, and that -2 is like how, related to retail is this word, or something like that. They represent something high level, which should contain the meaning really of the word, rather than this just kind of, this just purely very mathematical representation of the word on the left.
Okay, cool.
So those word embeddings, they are the final representation that we want to have of each word. For every single word in which we hope to understand, you need to have a word embedding. The question is, how do you create those word embeddings? There are a few ways there's a bunch of ways to do it. There are a few algorithms which are specifically designed to create word embeddings, like word2vec, and that's kind of the original word embedding algorithm. It works as such at a very high level. Initialize random embeddings, take pairs of words that appear close together, calculate their similarity using their random initial embeddings, and then maximize the similarity between two words using gradient descent. So it's basically you have like a one hidden layer neural network. It's equivalent to that. You're passing in the representation of one word. You want it to predict this neighboring word is likely to appear nearby with high probability. So I'll leave you guys to explore that. It's not too important. What we're going to look at is how they can be learned by other models and pulled straight off the shelf. So whatever that model, whether it's Word2Vec or whether it's BERT, we can get them off the shelf. And BERT is an example of a model which has learned a representation for a specific problem. So in PyTorch, you may find this embedding layer. The embedding layer is the kind of thing that you might see in a lot of models, and it contains all the parameters which represent the different word embeddings which this model can understand. So you might have, if you've got 100,000 words, each with 128 dimensional vector word embedding, then this layer would have that many parameters. This layer is essentially, as it says, a simple lookup table that stores the embeddings of a fixed dictionary and size. So basically every row is a different word, each column is a different element of that word in the, of that word's representation. And if we jump back to the notebook, actually let's jump into the practical now. What I want to do here is basically show, let's take a look at BERT and get the embeddings from inside it. So if we run the cell above, up here, this runs and this gets the BERT model, just gets it from pre-trained in Hugging Face. And down here, you can run this and print the model modules. BERT's a pretty huge model, so you can see it's got a lot of different layers in. And the first one you can see is that embeddings layer. So this is where we should find, or this specifically, is where we'll find what representations this pre-trained BERT has of the different words that we've got. Now, the pre-trained BERT has pretty good representations of words, so we should find that similar words have similar vector representations. And what I want to do is take these words out and try and visualize them using TensorBoard. So the first thing I want you guys to do is take a look at this and just make sure you can answer those questions. And then on the next cell, print the shape of the word embeddings matrix and make sure you can understand what's happening here. Once you've got that, then we're basically ready to try and visualize these word embeddings. So go ahead and spend 10 minutes doing that, and I'll wander around if there are any questions. Yeah, so for every word you've got fixed size. And that means later that whatever the word is, you can also essentially
So like each number has its like own defined characteristics. So it's like, for example, like 16 it's like the second number represents some
Yeah, it represents some high level feature about it.
Yeah.
What does it represent? I don't know. Yeah, maybe there's a way you can figure that out by looking at which words have high value there, and then trying to see if there's any commonality between them. Maybe we can do that next. If we can visualize it, it might be easy actually. Yeah, so this is just this is actually it's the dot there. So if you multiply that, you'll get all of this, and that's a sequential by function there, which does not those things one by one. So all these steps, that's what transform into the actual verb is actually also word, but adapted to the context. So yeah, so this is actually the embedding. That's just that layer there, that's the embeddings. And what's the next step? The next one is the position embeddings. That's adding information about which position of the sequence this was. So we'll talk more about that on so the word embedding is initially like it's just a random set random representation random representation all the way down to the parts. Those are parameters. So you don't have any meaning of you don't have any saying what those what we use for representation were. You just know that given different indexes of word one, two, whatever. This row in the embedding corresponds to so we update these parameters so that they become useful representations for each of those rows. And for all sorts of words. Yeah, it looks like it's decoded each time, but it's still actually practice. So you can see the individual work. Can't use key code because that not only what key turns it into the word, but also splits it up. So you want to get a vocab, look at the vocab, which is what yeah, that's I'm not yeah. There are, yes, why do you think they got that? is a block. But basically, there's so many it shouldn't be applied twice, so you should remove it from the model. And the reason why you don't have to apply it is because of the rest of the process stacks. Stacks the business. What value it does is it sets the dot. So well, it depends which loss function you use. If you use loss, don't put if you are using the first part, you know what? It's the way the model why so this is what the model looks like, and the indentation here represents of the model. So this is what we call embeddings. That is its class for embeddings. And inside that, that's what we think. Word embeddings, position embedding, token embeddings, layer embedding. The hard is the model got embeddings will drop out and get that last torch layer. That's all will be returned by that. And each of those things is just a byte. So if they're a ground line model, they'll probably have a dot link or a dot bias, and those are the parameters. So that's what model does. That gets that layer, you've got the weights, and then you've got the sound. So one's got the check. So that's not true. It's not to do that. What it's to do is to remove it from the you might call it previously up the different in the block, but we're going to get these embeddings out. They're still kind of off. These if I, for example, like delete one of them or multiply them. That's the value still going to be the bottom. I don't want that my playing around with the weights to be updated, changing these parameters. What I do got these captures will be a new list. It gives a new set of weights which are totally attached from the graph I'm going to is quite. So it's like, let's say for example, I have a hearing number, I want all these maybe living in the network, difference between different examples. So the same neural network, I pass one example through, I pass another example through, I guess if I want to have a example of an element of something, and when I do that, I can find a function to this variable that's in the middle of the velocity. And so now if you got that to it might like connect my new function. So basically just pick the parameter out. So they go yeah, exactly. So maybe I'm showing you after that. But for now, just basically remember that it's a new those parameters get embedded. Get embedded where so that letter embeddings go on embedding weight. Those are the representation free for us. And what we want to do is plot that like that. On the visual on the screen. And then you can compare them, you can see what's smaller, you can see what's out. You're right. Cool.
Yeah, so I've sort of not too much getting out there and all that. And also, like I say,
I'm wondering how people do this. Yeah, I'm waiting myself. I'm waiting on
you know, like I've used my face a few times, like something like this, it's just in that direction. You know, try doing it in the past. Yeah.
So that's not the number there, that's just like Okay, I saw a bunch of good questions there. Want to demo some of this stuff down here and highlight exactly where this comes from. So what I've got here in the next cell is basically just the number of embeddings that I want to get out of my model. I don't want to use all of them because because it takes long later. But then I've got this line, model.embeddings.wordembeddings.weight.detach. What does that do? Where did I get this from? Where does that come from? How did I know that was the part of the model which had the embeddings in? Well, in the cell above, I printed all of the modules, and in the top, you can see I've got this embeddings. So these are the different layers of Torch and of BERT. The first one is this named layer. It's called embeddings. The next one is this thing called encoder. So if I get .embeddings, it's going to give you all of this, and all of this is just one big Torch transform. And it has these attributes inside. It has the word embeddings attribute, it has the positions embedding attribute, it has the token type embeddings, etc. This is the one that contains all the parameters which represent the representation of each of my different tokens that BERT understands. So I've got 30,000 of them by 768. So to get those parameters out, if I want to actually get them, because I'm going to try and plot them later, I would do this. And that gives me a PyTorch layer. Then I want the weight from that. We saw that, I think, in one of the first lectures was, you can look at the different parameters, .weight, .bias, and you'll get the values in there. And then I had this funny thing on the end, .detach. What does that do? Can anybody give me an explanation of that? Yep. Mm-hmm. Yeah, potentially, yeah. So I want to update. I want to prevent me changing this thing from affecting the model, because these are like model parameters which I've got here. If I didn't do .detach, I'm like playing around with the model parameters. So if I like add 1 or something, it's gonna skew the whole model. Or if I maybe compute something from this value and then do .backward, it's gonna update not only the parameters which I was doing something with, but also the parameters of BERT earlier in the model. So you want to do .detach to create a new instance of these parameters and store them in a new variable. And so that's what I've got there, this embedding matrix. This line, what does it do? Easy one.
Just take the first 30,000.
Exactly, yeah. So in fact, there's only a few more than 30,000, isn't there? As we'll see in a second. But if you wanted to truncate it, make things faster, then you could just slice off more of them.
Just for understanding, could you replace detect with deep copy?
Sorry, what?
Could you replace detect with deep copy?
I'm not sure the torch tensors have a .deep copy method, but it does the same thing. It does the same thing basically, yeah. Copies and makes a new instance of, yeah. Cool. So here's my embedding matrix, print embedding matrix dot shape. Run that. That's my shape. This represents how many words I've got the embeddings for. This represents the embedding. And then this is where we played around with the vocab. I looked at the vocab. You can see everything in there. So let's so once we got this vocab, which is a dictionary, I can index it with different words, and I should be able to see the ID for that word. Where is it? There it is. So the word hello has ID 7592, and you could do that for any other words you want. If I give it some broken word, it's still going to give me an ID. No, it's not, sorry. If that's because it's not, it doesn't recognize it. Instead, this word will be represented by unknown. That token unknown is token number 100. So during the tokenization, when I turn my strings into the unique IDs, I'm gonna replace anything that's unknown word, or unknown token with this. So knowing that, we can map between the different IDs and words to understand in this embedding matrix, row 500, what word does that represent? Row 600, what word does that represent? But I can't go from ID to token here. I can only go from token to ID. That's how get vocab works. I think there's another method for this. What is it there? There's so there's convert tokens to IDs, convert IDs to tokens. I could use either of those, or I could just reverse this this dictionary. So later we'll use that. Okay, cool. So that's just a for loop that's going to print the different values. And down here, I've got a function. I've got a function which should, if the visualization works in TensorBoard correctly, it should take my embeddings, missing spaces there. It should then call this function, which is going to create labels for the embeddings. This is a bit fiddly, don't worry about it, but it'll basically allow us to highlight words by their length or by the number of vowels or by whether they're a number, so that we can compare whether those groups appear similarly or not. And then down here, we've got this visualize embedding function. All it does is it uses TensorBoard summary writer, add embeddings method. And this one takes in the embeddings and their labels and the label names. So let's see if we can get this to work. It's going to run, it's going to perform the embedding, it's going to take the embeddings out of the model, it's going to put them in TensorBoard and should show them when we run the next cell. Cool, embedding done. Let's run this cell here. This shows up. Yeah. It's 30,000 tensors. Each of them has 768 dimensions, so it's pretty big. The only thing you need to be careful of is that this is correct. What was that? You can do this. I'll show you what this does in a second, but basically these are just ways to label the data. So in a second, you'll see I can basically show a drop down to show the ones which contain different numbers of vowels or contained by length, or you could say, you know, you could get a list of animals and basically say, if this one is an animal name, look at that. So here, and this might make a good social post if you want to take a picture of it. Here is a visualization of all of the different words represented by Bert in 3D space. It's been projected down into that 3D space. And there's a lot going on there. What's the cluster? Yeah. I'm going to let you guys have an explore around with this, right? Because there's a lot of interesting stuff that you can do with this. But just so you can see how the code which I wrote, which took me a real long time to figure out how it worked, by the way, this thing up here, just so you can see how this works, here's the name of the label, and here's how you calculate that label. And then in TensorBoard, you can change this so you can see, or you can color them as such, right? So here is everything colored by the number of vowels, or it's colored by whether it's a number or not. So there you can see there's all the numbers. What are all of these things over there? I'll let you figure it out. And feel free to apply some of your own functions to determine what different parts of this mass represent. So you've got two drop downs here just to explain this. Yeah, you've got the label by, that's what shows up when you hover over it. And you've got the, I forgot to get rid of that now. And you've got the right-hand side drop down, which is the color by. So you can color by length, and you can see something like that. Looks suspicious. What's going on there? So take 10 minutes, run that. If it doesn't work or you can't figure out how to run it, let me know. I'll come and help out. But yeah, so go over here and then go down to projector.
Sorry, one question.
Yeah.
So how did this projection work?
How did what, sorry?
How did this projection work?
Great question. So this is a principal component analysis of the 768 dimensional vectors. So you've got these 768 dimensional vectors, and you basically want to say which directions do they vary most in, and the top 3 directions, take those as the x, y, and z coordinates. What was that?
We started low. So
Yeah, they were only. So they all going to one.
Because there is yeah, so
But it's
yeah,
there's 26 classes. That goes. To the meaning of the
Yeah, so maybe I should
Has anybody managed to implement like a nice function which shows some grouping? Yeah, what? Oh, that's the opposite of what I wanted to hear. We'll come and fix that in a second. I just wanted to point out something for those of you who are wondering what's happening here, because there's a lot of numbers being thrown around. 768. You got this 3D space. You got 30,000. And there's something about PCA, so I wanted to bring all of that together. So what we're looking at here is a 3D projection of very high dimensional, 768 dimensional vectors. So of course you can't visualize something that's 768 dimensional. The way you should think about it is just, okay, it's like 3D, but with more axes, okay? It's like an arrow in this space, much like an arrow in 3D space, except there's many more dimensions. And so PCA is a technique, a dimensionality reduction technique, that's been used here to project the most useful components into 3D space so that you can visualize it. How does it work? It works like this. I'll try and do a little illustration. So let's say you've got this 2D axis. Looks like this. And in this 2D axis, you've got some data which looks like this. The data is all along that line, okay? The data is all along that line. And the thing with that is that, well, I've got 2D data. Each of it has an X coordinate and a Y coordinate. But there's actually not much use in having both those coordinates because they're totally dependent on each other. And what would make sense is that I say, okay, well, really, I should just use this as the X coordinate. And I should take these axes and basically rotate them like that so that I can represent all of my data along one line. And I can just give the X coordinate because they all have the same Y coordinate. That's what PCA is doing. Roughly, it's just resetting the coordinates in the direction which the data most varies. And once you've done that, you can throw away the higher dimensions. So like here, I could throw away the y-axis because there's not much information included in that direction at all. In fact, it doesn't vary at all. So this direction here, we call this the principal component. That is the direction the data varies mostly in. And you could do that with in much higher dimensions as well. Now, sometimes you'll have not all the data sitting on just a line, but the data sitting maybe around a line. Sorry, laptop is particularly slow for everything running on it, streaming on it, recording and computing all at the same time. So you might have data not just on that line, but kind of around that line. So in this pure case, the green line has actually no variance in this direction at all. But you might have some data which hovers around that. Now that means you can't just throw away the other axis. You are going to lose some information. But if you do that in decreasing order of which direction they vary most in, you should only be left with the most important components, the three most important components if you project into 3D. And that's what we're looking at over here. Okay? So to run through that just one more time. What happens when you do PCA is you take all the data, you calculate its covariance. That is a set of axes which point orthogonally from each other, and they tell you in each of those directions how much does the data vary, and then you just remove them in increasing order. So remove the direction where the data varies least, and then second least, then third least, until you're left with these principal components, and that's what these three are here. So hopefully that sheds a little bit of light on here, but that's how you go from 768 dimensions to 3 dimensions. Note, a lot of information is lost. Like almost all of it is lost by doing that. You can see that down here when you look at the 3 different components. You can see, okay, here's the 10 top principal components. The first one captures 6.6% of the variance. The 10th one captures 1%. And total, in 3 dimensions, we've captured 12.12% of the variance. So 87.8% of the variance is you can't see that here. It's been thrown away because we've had to sacrifice things in order to be able to visualize them. So this is the 3D production of that space. All right, I'll run around again and continue with that. We've got a bunch of time left. I won't see notifications. I've been tagged in something. This is really cool. This is a great shot right here. Me in it. What's TSNE? TSNE is just another dimensionality reduction technique. One where I believe it is points in the original space remain close in the projected space. Is the key property. Very complicated. I don't know too much about it. Wouldn't worry about it. It's basically a dimensionality reduction technique. But it does it iteratively. So if you really want to burn out my laptop, you can click this, and it will try and visualize the PCA algorithm progressing, which is not just a one-off calculation. It does it iteratively. So in a second, you see something really cool. Whether it's useful or not really sure. So initializing TSNE. Now, now's where I could really do with the GPU, but all of that is moving. And it's going to try and cluster together similar parts, I believe. What does it mean? I don't know. I'll look up there.
Yeah.
Yeah, it's not. I only got this by so I think I also see this and inside of it. Yeah, so these are I'm not getting inside of something and so you can't index so those or in case the way it works, basically schools are big. I haven't really worked with it. So I haven't really worked with it. And it's really full of as I know. So it has that brand. So if you've got brands, one thing you're going to get away with is and that's the really hard. That's the dimensionality. Yeah, that's index. Yeah. So this is just about well, after embedding, so they do stuff inside of embedding, then it's going to pass up the whole point of work is to code. So I set up existing values into another set of existing values. But even just like this,
So it's sorted by the goals. So your model has been
That's I'll message my guy. Well, I'll test my back. Try it again as well. Try it. Maybe, yeah,
So, did anybody find out what any part of this is? What's going on here? Anybody find anything interesting? We can zoom in on it. We can select it. We can create the function to define how to label it. Anybody find anything interesting? Unusual label, did you say?
Label with
Yeah, yeah. So,
that represent like words which like are not real, like something that you try to say.
so the question is, does unused, which is something that shows up in the vocab, does that represent, where was it? Well, if you print out the vocab, it contains a lot of words which are covered by square brackets, indicating they're special tokens. They're called unused. They're not words which are unknown. Unknown words are represented by the UNK token with square brackets either side. The unused words, I believe what they're for is for when you fine-tune BERT on your own data set, you may have words which come up in your context much more than they do in general. So they might not exist in the 30,522 embeddings that BERT has learned. So you could fill in those embedding layers, those are unused token representations with something that makes sense in your case. Essentially, you can add to the existing set of representations which BERT has using those fillers. All right, so I mean, there's something quite obvious happening over here, right? If I color them by length, all of these are 3 long. And if I label by the word, you can see these are all the unused tokens. What is this actually? Oh, this is sorry, I'm coloring by the number of vowels. So down here you can see these are all the unused tokens. They have very similar representation. They don't represent much, really. What about all these pink ones over here? They're all numbers. All numbers over there. These blue ones, not sure. It's like more numbers. Yeah, they're just 4-digit numbers, aren't they? We can look at is number. So you can see here, all these red ones, they're all numbers. The others are all words. This is really where the interesting stuff is. Is there an observation? Cool. Nice. Anybody find anything interesting? Okay, well, I mean, if you click on any word as well, the next thing I want to show is it shows you the words most similar to that in the original space. You can see they don't look very similar in this projected space, but if I click aristocracy, the next word that shows up is nobility, aristocratic, elites, etc. You do that for any word, and you can see which are the closest. So essentially, this is a nice little similarity search tool built into TensorBoard, which can be nice for understanding, okay, are your embeddings reasonably accurate, and yeah, and then kind of where does different stuff show up. So that's that. Clear selection over there. So I'll leave you guys to play around with this function here. Again, what this is the name of the label that you want and a function which takes the word and computes something from it. So it could be like, is in my list of animals, or is a preposition, or whatever else. So please play around with that and explore what this visualization of BERT looks like. We've got 12 minutes left, so I want to introduce one final challenge, which I'll leave you guys to go and work on after this, and that is this word analogies notebook. If you open up this notebook, I want you to explore this. This notebook walks through the illustration of showing how these word embeddings can capture analogies in words. So if you have a word analogy, which is something like A is to B as X is to Y, then you can kind of compare like, right, well, what's the difference between A and B and how is that applied to different words? So for example, London is to UK as Moscow is to what? Cat is to kitten as dog is to what? Does this kind of vector math work out in embedding space? And this notebook's an illustration of the fact that it does. The way that works is we take BERT, we get the pre-trained model, we get the BERT tokenizer. Take a look at that in Coda there. Print out the modules again. Get the embedding matrix. Something's gone around. Not found transformers. You know what to do there. Just pip install transformers. Run that. Install transformers. Run the next cell. All the way down here. This is the visualize embeddings function that we used in the other notebook. And then here is a function which gets the word embedding given a current word. It basically indexes the embedding matrix for a particular row. That's the embedding for that word. And so it gets that word embedding. What that means we can do is you can, well, what we want to do is be able to look up the nearest tokens to an embedding. So if we got a word, we use that function just defined to get the embedding. And then we go through all the other words, look at what their vector embeddings are, and compare those two vectors. You can do a cosine similarity to compare them for similarity. And that'll be a measure of how similar are these words. This function basically goes through each of them and gets the most similar n words. And this function here, just down below, is the analogy solver. So I don't have torch metrics either. So let me just install that. Pip install torch metrics. Run that function to get the word embedding. There's all my, well, there's one of my word embeddings, just one, massive. Get the nearest word embeddings. What am I printing there? I'm just showing the similarity indices, which I've calculated there. And this function is where the bulk of things happen. So this is the function which solves the analogy. It says A is to B is what C is to D, given A, B, and C, and returns D. So essentially takes an A, B, and C, gets the word embedding for A and B, cat is to kittens, calculates the difference between those two representations, and then it's going to add that to the third word, C. So it's going to add that transformation vector on and comes up with a final embedding. Then the challenge is, what's the nearest word to that embedding? And so we basically iterate through the data set, find the nearest embeddings, and print out the top n tokens. So if I run that, define that function, down here you can see some examples. So I solve the analogy. Man is to woman, as king is to queen, is the top pick. And then you can see the top 5 related after that. London is to UK, as Moscow is to, UK comes out first. Puppy is to dog, as kitten is to dog, dogs, cat, right? So you can see it might take a few, it's not perfect. And funnily enough, in a lot of cases, the closest word is actually the original word, which is why it's got this, this skip line over here as well. So play around with that and make sure you understand that. And once you've gone through both these exercises, I think you'll have a good idea of what the word embeddings represent, especially once you've played around with looking at this and coming up with different functions to explore that. But you can see similar words should appear similarly. And this analogies notebook is an application of using that visualization. All right, cool. So have a play around with that. Skip through that that analogies notebook for a second, and then we'll wrap up. All right.
cells above, and then do exclamation mark.
Yeah, it's just yeah, yeah, no, it's fine.
I did that. It's already satisfied. When I find it, it's
All right, we're gonna wrap up. Any questions? Anything final to end on here? First day, Saeed, Oxford. Anything? Questions remaining? Anything you want to demo? Cool. Well, we should be good then. We've only got one more thing to do, so I will wrap up this stream and then we can get on with it.